Welcome to Chapter 4 of Physics Without Calculus for Aquinas University. We'll be going over the OpenStax text, College Physics, second edition, Chapter 4, Dynamics, Force, and Newton's Laws of Motion. As previously stated many times, I will be giving a brief overview of the slideshow created by OpenStax, as well as referencing the actual text that's available to you. I will be going over selected problems from the textbook. I will not be going over all of them. At any point, please pause the video and go over those if you'd like more practice on them. If you have any questions, shoot me an email or comment down below. I'll try to get to those as often as I can. And with that, let's begin. So we're going to talk about dynamics, as I said. Dynamics more or less describes motion and how it works, why it works, and the way it works, right? We talked about vectors and stuff like that before, describing motion on a Cartesian coordinate system and polar coordinate systems, etc., etc. This is sort of the science, the sentences, right, behind the math is what we're going to kind of get into here. Here we have a picture of a dolphin. The way the dolphin moves is described very well by Newton's three laws of motion, which we'll get into. So when we go through the wording for everything and the math behind it, try to, in the back of your mind, picture how this stuff is actually working. Like you're probably sitting right now at a computer watching this lecture. How does you sitting in the chair and the chair sitting on the ground reflect what we're talking about here? Because it does. Newton, of course, Isaac Newton, super famous scientist, probably one of the most famous scientists to ever exist. If you ask someone to name a scientist, there's a good chance they're probably going to name Newton, right? He wrote this book here, which I'm not going to try that Latin. I don't speak it, in 1687, and kind of more or less started a lot of what we nowadays call science. He had reasons for what he stated, which was sort of a new concept at the time. And scientific history is super cool. Researching Isaac Newton is more interesting than you think it would be. So it's worth looking at. So when we talk about Newton's laws of motions, we apply them to the physics we've talked about from chapters 2 and 3. We're going to have to bring in ideas such as free body diagrams. Free body diagram is, in essence, what is happening in a system or to a object, and how those interactions work to produce the total outcome. The example shown here is you have someone on ice and her friends in pink are pushing her for some reason. And even though the friend with the dark hair is pushing to the right from her left, and the friend in the brown hair is pushing up from the bottom, she's actually going to go sort of a northeast direction. Why is that? Well, we take into account, as it's shown there, F1, F2, and we can create an understanding of the direction. But sketching out people with buns of hair and shoulders and all this stuff is unnecessary, right? So A is what's going on given a particular question, but B accurately represents what's going on as well. And you're taking away all the nuance of skaters on ice and hair colors and all that jazz because it really doesn't matter the question, right? So understand how to create a free body diagram and thinking about every possible thing that could be in that free body diagram. The idea behind doing that is easing the math and easing your understanding of the topic. Cool. So that's free body diagrams. You've probably been doing them already, but that's the name of them in case you didn't know. Cool. So let's take a look at Newton's first law of motion. Newton's first law, as shown here, says a body at rest remains at rest, or if in motion, remains in motion at a constant velocity unless acted upon by net external force. So if something's not moving, it's going to not move unless you do something to it. If something is moving, it's going to continue to move unless you do something to it. And U means any possible force. That is Newton's first law of motion. How does that apply? Well, here we have an example of a spring, right? If you don't do anything to the spring doesn't do anything, right? If you apply a force to a spring, say pull it out or push it back, then suddenly it's doing something and it will react accordingly. That's the idea. The fact that things don't move when they're not moving is like a mathematical concept. It's something that there's numbers and Greek letters behind. And that idea that you can describe something not moving with math was kind of a concept Newton more or less was foundational to. Not because they created it, but he was foundational to it. And here we have examples of how all of this plays, right? This, I believe, is a question from the textbook. I'm not covering this particular question, but you have a simple act of pushing someone in a wagon, right? The act of pushing someone in a wagon has connected math behind it, and the math described by what you're doing can be complicated and can be, once you decipher it, solvable, right? If you know, for example, how heavy the cart is and how fast the wagon cart person is moving, you can derive a bunch of information like how much the people pushing the child in the wagon or cart is, how much force they're impacting. Like, that's all stuff you can get. And what's cool here is if you look at the center at the top 3x diagram, they have an F1 and an F2 there going off to the east. That's interesting because since the two people are pushing the wagon in the same direction, they're both adding force to the system that is the wagon and the kid inside. Even though the person in the pink shirt is pushing the wagon, the person in the green shirt is pushing the wagon sitter, right? They're both pushing the thing in the same direction, and the person in the blue striped shirt and the wagon are essentially acting as one thing here, so we can squish all that down to one red dot and describe all forces related specifically to that one red dot. 3x diagram, right? Again, you've been doing this already. I'm 100% sure of it. But when you're asked a question that has real world examples like ice skaters or people pushing things, right? You don't need to draw stick figures of humans and give them hair color and all that jazz and shoes. Draw a 3x diagram. So that brings us to our second example, Newton's second law of motion. Newton's second law of motion is actually an equation as well, funny enough. It states that the acceleration of a system is directly proportional to and in the same direction as the net external force acting on the system and inversely proportional to its mass. So, in essence, the ever common phrase F equals ma, force equals mass times acceleration. And of course, you can rearrange that acceleration equals force divided by mass and stuff like that. But that describes a lot of the interactions that go on in nature. For example, as we see here, this person is pushing a basketball and the basketball moves, right? If you take a basketball and you pass it to someone, the basketball goes flying, not you. But if you get behind a large parked car and you apply that same force, the car is not going to move the same speed and distance that the basketball goes. You can't pass a Volkswagen the same way you can pass a basketball. And the reason is there's a big difference between the masses of the basketball and the car, and therefore there's a difference in the acceleration proposed, even if the force is the same, right? If we take A equals F over M, and if you make the denominator M very, very large, that by definition makes A very, very small, right? The acceleration. So everything feels an acceleration when you go try to push a tree over. The tree is feeling what's happening, but the tree, if it's a big tree, is so massive you don't knock it over, right? But if you go to a little twig and you push it over, it falls over. That's how that game is played. That's the equation behind it, F equals ma. And it's also worth noting here, whenever you talk about force, at least in this class, the unit of force, the SI unit of force, is the Newton, abbreviated capital N. And a Newton is 1 kilogram per meter over second squared. 1 kilogram meter per second squared. The amount of 1 Newton is the amount of force it takes to move 1 kilogram 1 meter per second squared, accelerated. So, yeah, that is Newton's second law of motion. Everything that moves, any force that impacts that causes a change in displacement or an acceleration, Newton's second law of motion describes it. The fact that it's moving is described by Newton's first law of motion. So Newton's first law of motion says a force needs to happen in order to do something, and Newton's second law of motion describes how that force is doing the thing. So let's take an example, 4.2, and we can go over some of this math. Here we go. So what rocket thrust accelerates this sled? And also this in the third law of motion, I actually explain how rockets work in a vacuum, by the way. But question, prior to space flights carrying astronauts, rocket sleds were used to test aircraft, missile equipment, and the physiological effects on human subjects at high speed. There's videos of this. It's hilarious. I highly suggest you YouTube it. They consisted of a platform which was mounted on 1 or 2 rails, like a train, and propelled by several rockets. So stick a bunch of rockets in the back of a train. Calculate the magnitude of force exerted by each rocket, called its thrust, capital T, for a 4-rocket propulsion system as shown in the picture. The sled's initial acceleration is 49 meters per second squared. The mass of the system is 2,100 kilograms, and the force of friction opposing the motion is known to be 650 newtons. Cool. So what's going on with this entire conversation? Well, a lot, right? But if you try to draw a free body diagram explaining everything that's being talked about, it makes life a lot easier. So the rocket and the rail and the testing aircraft and missiles and all that jazz, we're going to boil all that down to a single red dot in the center. That's a little bigger. And then we can say what forces are acting upon this rocket sled. Well, if you're dealing with something in reality, you always have gravity, or in this case, weight being applied to the system. And gravity or weight always goes down into the ground, right? For real world examples. So we have a weight down equal to W. And we're skipping ahead a little bit here, but whenever you have have a force in one way, you have an equal and opposite force in the other way. Hint, hint, Newton's third law. So that's where that N, normal force, is shown facing up. And then, of course, you have 4 rockets all doing the same thing in the same direction. So we're stacking those 4 thrusts to the east. And as said in the example, you have a little bit of friction opposing the motion, which is 650 newtons to the west, dictated by the standard of the equation there. So all that going on, how big are each of those T's given that acceleration, that mass, and that friction? Well, to solve this, we use an equation that has the question we need answered, which is the force to push it, the known of mass, and the known of acceleration. F equals ma. Fantastic. But the F in this case is all forces dictating the motion. Okay? So what forces are involved in this process? The sled is moving horizontally, again, jumping ahead a bit here. The sled is moving horizontally, not vertically. So I don't care about gravity and all that jazz because that's not the way the sled is moving. The sled is not moving up and down, so I don't need to care about those parts of the question. The sled is moving horizontally, left to right, east to west. So I do care about all forces in the horizontal plane. And if I look at my free body diagram, I have 5 forces in the horizontal plane, 4 thrusts and 1 friction. And the friction is the opposite way of the thrusts. So I can say my net force is equal to 4 times the thrust, because there's 4 separate thrusts of equal power, minus 1 F, and the F is friction. Since the friction is the opposite direction of the thrust, we give it a negative sign, right? So the net forces acting on this object is 4t minus F. And I know that F equals ma, so I can set my equation as 4t minus F equals ma. Cool. What am I solving for? I want to solve for the thrust. I want to solve for t. So rearrange my 4t minus F equals ma, throw my F on the other side, make an addition, and start plugging in my numbers. Let's go in here, substitute your values, 4.15. Substitute in my values. I find out that the total thrust of this rocket ship is 1 times 10 to the 5th newtons, or a lot of newtons, right? Meaning, if I divide that number by 4, I get the total thrust for each individual rocket as 2.6 times 10 to the 4th newtons. That's pretty impressive, right? And as you can see, the math itself is not overly complicated. A lot of this is drawing your free body diagram so you know what to solve for, finding an equation that allows you to solve for it, and then plugging in your numbers. With that being said, let's skip the thing I already talked about and discuss Newton's third law of motion, which states, whenever one body exerts a force on a second body, the first body experiences a force that is equal in magnitude and opposite in direction to the force that it exerts. That's complicated. That's a lot of words. This is the picture here, I think, does a pretty decent example of what we're talking about here. Here we have a swimmer, system of interest, kicking off of the pool wall to accelerate themselves into the water. So when you kick off of the pool wall, your legs and your muscles are extending out away from the wall, right? It's a spring. And you shoot off of the pool and into the water. What's happening mathematically? What's happening physics-wise when you kick off of the wall? Well, is it your legs that are like pushing you out? Technically, no. When you're doing that work, your legs are pushing into the wall, right? The force is being exerted into the wall. The wall, however, is bigger than you, and the wall don't move. So, since the wall's acceleration is basically zero, what happens to that force? Well, Newton's third law of motion describes it. When you push into the wall pushes back at you with the same amount of force. And since the wall doesn't move, its acceleration is zero, all your acceleration is given back to you and you shoot off. If you put less force into the wall, you take off at a lower rate. If the wall is not as secure, say it is like one of those above ground pools with the flimsy looking walls, and then the wall moves a little bit, you would get less thrust when you accelerate, because some of the force being put in the wall is being soaked up by the wall, pun intended, right? That's how that game is played. Your butt sitting on the chair, the reason why your butt doesn't fall through the chair is because the chair is pushing up on you equal to your weight. If that changed for some reason, you would collapse the chair. It's a weird concept, I get it, but it's cool to picture, right? Like every time you walk, you're pushing down the earth is pushing up on you, which allows you to walk. So let's do an example here, 4.4. Here we go. A physics professor pushes a cart of demonstration equipment to a lecture hall, as seen in this wonderful image below. Her mass is 65 kilograms, the cart's is 12 kilograms, and the equipment's mass is 7 kilograms. Calculate the acceleration produced when the professor exerts a backward force of 150 newtons in the floor. All forces opposing the motion, such as friction, air resistance, and everything, totals 24 newtons. So, what's going on in this scenario? Got this picture, you got all these random shapes for some reason, and I'm forgetting the name of that thing, the yellow bar on the tube there, makes static electricity. All that stuff. And, they gave her heels for some reason. I don't know. But all of that artwork, we condense it into a free body diagram, as we talked about before. We know that there's gravity because we're on Earth. We know from the conversation we just had, Newton's law of motion, if you're pushing down the floor is pushing up on you. That's where the W and the N come from. We know she's pushing the cart to the east here. And we know that friction's opposing her motion, so therefore friction's going to the west. So, cool, right? Is that the entire conversation? Well, not quite, right? System 1 is everything that's going on. But there is, in fact, a second system involved here, which is, as stated before, the cart itself. The floor is pushing her forward, but she is pushing the cart. So we can actually consider a second system, which again is just the cart, that's getting the force from the professor, it's getting friction back from the floor, and it has its own weight and therefore own normal force. So to calculate the acceleration produced when the professor exerts the force, we don't care just about, we can not care just about everything. We can care about what the professor's doing to the cart and then how much the cart is actually moving, because the cart doesn't see the force of the feet, right? The cart just feels the force of her push. So, again, I am I say this every time, right? I am a resource for you. The book goes into more detail than I'm going to go in these short YouTube lectures. Pause the movie, read the book on your own. If you're getting lost, that stuff helps. So, given Newton's second law of motion, F equals ma, we can rearrange that to solve for acceleration, A equals F over m. And then we can discuss what forces are acting on the system here. Well, the net force involved for the system, again, system 1 is everything, is given by the force of the floor minus the force of the friction. We know, I'm saying here, that her feet are pushing with a backwards force of 150 newtons. So if her feet are pushing into the floor, then the floor is pushing her forward, right? When you step, your feet go back. So your back foot is pushing off of the ground. So your foot pushes back and you go forward. It's super unintuitive to think about, but it's how it works, right? You walk forward by pushing backwards. So we could take those equations. We know the force she's putting on the floor is 150 newtons. Or the force of the floor pushing her is 150 newtons, because we're told that. It's in the direction we're talking about, so it's positive. The drag force, the frictional force, is negative because it's opposing motion. 150 minus 24 is 126 newtons. Equation 4.19 here. So we can figure out the mass of the system, the big system, by adding up the weights, 84 kilograms. Cool. So the total mass of the system is, the total acceleration of the system is A equals F over m. Divided out, we get a net acceleration of 1.5 meters per second squared. Cool. Does that answer a question? Well, it answers the question for everything, but let's take a look and calculate the force the professor exerts on the cart using the previous example. So that is the force of the entire thing. What about the individual cart, right? We can separate this into system 1, system 2. What is system 2? So we can take everything we've talked about here, and we can remember our equations are the exact same, right? But noting that the magnitude of the net force and of the net external force system 2 is given by what we just talked about, we want to know the force the professor is pushing on the cart, right? Calculate the force the professor exerts on the cart. So the net force is equal to the force of the professor minus the friction. Therefore, the force of the professor, rearrange the equation, is equal to the net force plus the friction. We know the net force is F equals ma, and we can calculate that because we just figured out A. So plug and chug everything back out. The professor is exerting 53 newtons of force to push the cart. even though the professor herself is pushing 150 newtons, but with her feet, the cart's only taking 53 of that. So where's the other force going? Right? So we talked a lot about that normal force, that force of gravity, right? That is, I'll show you in the book here, gravity, weight. Normal force in these equations, the N and the W I've been talking about, the W stood for weight, the N stood for normal force. Normal, to remind you, is like perpendicular, essentially, right? When you, well, perpendicular to the ground, anti-parallel to the force. So anything that is in real life has a gravity to it and therefore has a force pushing up. I'm sitting down in the chair is pushing up on me. My weight is going down, the chair is pushing up. The chair is normal force to my weight. This is important because that can give us, as shown here, tension and drag force or friction. These are determining factors based on how heavy something is. There's this interesting part here if you want to read common conception about normal force versus Newton's. It's worth a quick check out. So a classic example we see in physics is the skier going down the hill, right? You can determine a lot of questions and solve a lot of problems based on knowing things such as the weight and what have you. This is a question in the book. I suggest you do it if the example I work through doesn't make sense to you. It's trigonometry. You just got to remember your triangles. Free body diagrams are fantastic for this, right? The part on the right there. If you can draw a free body diagram that accurately represents what's going on, you can solve all the equations relatively easily. Right? The math is the same for all of these questions. It's just drawing the diagram to understand how the math interacts, what's negative, what's positive, what's a sine or a cosine, right? All that jazz. And that best comes from, again, getting your thetas. So there's questions in the book. I suggest if you want to go through, check them out. They're super interesting. They're beneficial to you if what I cover isn't enough. I keep saying that, right? I am not the end product of your studying for this class. I am simply one of the resources you have at your disposal. The example I will be covering is 4.6, the tightrope one. And I believe I actually gave this as a question in the homework. So kudos to me for doing something like this, right? Calculate the tension in the wire supporting a 70-kilogram tightrope walker as shown in the image here, right? This image gives us a bunch of information. And when we say that, we can kind of picture a tightrope walker. What happens when you walk on the tightrope? Well, the tightrope bends a little bit. In this example here, the weight of the tightrope walker causes the wire to sag by 5 degrees when he's in the center of it. And since the system of interest here is the point where the wire and the tightrope walker are centered, we can draw a free body diagram for that walker for that exact little point. And figure out the question at hand, namely the tension. So tension is a way of describing force, right? So we could take our question that we're talking about here and we could break it down into its subsequent parts. We know there's a 5-degree angle, and we know that there's a left and a right side to the rope. So take what we talked about from previous chapters here. You have your hypotenuse, you have your long section, which is the rope itself. But since there's a degree angle there, you can break it down into its X and its Y components, and then you can use those X, Y components to solve the questions, which is here why they have, actually, I think there's, yep, here we go, which is here why they break it down into its parts. I can't remember the word now. Oh, Lord. Break it down to its TLX and its TLY, TRX, TRY, right? So you have an X and a Y component to the left and the right side of the rope, And then when you put those into your free body diagram, you then, as I just stated, right, can throw them in the correct locations. The red dot there represents a tightrope walker, and he has left and right components of the tension, essentially holding the rope together. And then he has the rope pushing him up a certain amount and his weight pushing it down a certain amount. Noteworthy here is we're not given this in the question, but we need to remember these things. If you're not moving, if your acceleration is 0, your force is 0, right? Newton's second law of motion, F equals ma. If a is 0 because you're not moving, because you're not accelerating, or whether you're not accelerating, you can move and not accelerate, but if you're not accelerating, then your force is 0. And it takes a force to cause an acceleration, Newton's first law of motion. So if we take all of these components, net Fx equals 0, net Fy equals 0, and our free body diagram breaking down the rope into its constituent parts, we can solve what we're talking about here. So that's kind of going over 4.44 and 4.45 is what I just talked about there. So given the trigonometry here and our sines and cosines for our x and y components, we can solve for the tensions of the various parts there, right? So the cosine of 5 degrees equals TLX over TL. And same thing for TRX and TR. Setting those two equal to each other tells us that the tension on the left side is equal to the tension on the right side, and that's our total tension. That makes sense when you think about it, but the math here verifies what we're talking about. Because the angles are the same, therefore they're both contributing an equal amount. So consider the vertical components subscripted by y, right? We can solve for t. So we know that the net y is 0 because you're not moving. We know also from our diagram here that the only things working in the y motion are the left and right ropes, y component, and your weight going down. So we can set up an equation to where the left and right y components of the tension minus the weight equals 0. And we know the left and the right components of the tension in the y direction because they're the sine of 5 degrees. So 4.51 here, your F net in the y would be therefore equal to 0, which is equal to t sine 5 degrees plus t sine 5 degrees minus w. Rearrange all that jazz to solve for t, and you end up with a tension of 3,900 newtons. Cover this a little bit, but just to emphasize it, your weight is equal to your mass times gravity because your weight is a force and your acceleration is gravity. So F equals ma. Right? So again, breaking it down into small parts, look at your free body diagram, extracting from the question more than just what's given to you. It doesn't tell you that your forces are equal to 0, right? You have to infer that by the fact they're not moving. Will get you to a pretty easy question because all it is a little bit of trig and division. Cool. So you can change the orientation of all of this, and you still end up at basically the same conversation. And what we just talked about there kind of goes into the math of lots and lots of engineering, right? If you ever seen a suspension bridge like here, the Golden Gate Bridge or the Mackinac Bridge in Michigan, right? Those are the road and the cars are just held up by cables and a couple little posts, right? Well, not little posts, a couple posts, the big towers in the center. It's all tension. That stuff is all mathematically calculated, and these bridges have been lasting for a very, very long time, right? And it's the math for this bridge is a bigger version of the math we just did there because it's the exact same thing. It's tension, it's weight. Cool. So going on a bit here, this is another example of understanding this weight tension conversation that we're having here. Here's a Tarzan, I guess, hanging from a vine. Okay. But when you look at this example here, you can see that the arrows are used to represent the forces, right? We've been doing that. The tension in the vine above Tarzan, F of T, is the force he exerts on the vine, and his weight down below is equal to his tension. It's equal to his tension because he's not accelerating. If you're not accelerating, your force is equal to 0. So suppose we all given the eight man's mass and asked to find the tension of the vine. That is easily done, as I said, because if those two equal 0, those two must be the same number. His weight pulling down is equal to the tension applied to the vine because he's not moving. If he was too heavy, the vine would be breaking, right? And he would be moving down. Once you kind of get the math is pretty easy. All of this math at this level, right? We're not caring about the 1,000 other mini little components to it, is draw it properly, think about it, find your equation, plug it all in. If you ever seen tugboats pushing barges around, right? Seems super complicated, but if they think about what they're doing, they can do quite miraculous things with just a couple little tugboats shoved in the correct location. And if they don't plan out properly, you get that thing that happened a couple of years ago where something was caught in, was it the Suez Canal? I think they had that giant boat like across the side of the canal, right? That's what happens when you don't do your math properly, and it kind of halts all economy in the world for a couple of days. All right, so I think this is my last example problem. Yes, this is my last example problem. I'll go over a notorious question in physics, which is the hanging light problem. There's lots of equations, lots of trig, and it's always daunting to students. But as I said already, if you take your time when going through these problems, you will realize they're very doable. All right, here we go. So different tensions at different angles. Consider the traffic light. This traffic light, say, is a mass of 15 kilograms, suspended from 2 wires as shown below. Find the tension in each wire, and we're going to not care about things like the mass of the wire for this. Okay, so what happens here? We have a wire shown with 2 different ropes at 2 different angles. Oh, this one's actually bigger. We want to know the tension on each rope. Previous question that we worked through, the tension was the same because the angles were the same, right? We showed mathematically that they were the same, but at the end of it all, it was just mass divided by 2, essentially, right? That's not as easy this time because we have a bunch of stuff going on. We know the mass of the object, we know the angles, and that's all we know. Can we still solve it? Yes, we can. So your first thing is to understand what's going on and then try to draw it in some way. There's a lot going on in this conversation. If you look at figure D over here, it has all these different directions and breaking down components. But the important characteristic here is any direction is simply a combination of X and Y components. So if you break down that 45 and that 30-degree angle into X's and Y's, now everything is in either the horizontal or the vertical component, and then you can simply add and subtract them based on where they're pointing, which is what E down here is. What is pulling down? Its weight. What is pulling up? The Y components of each rope. What is pointing to the left? The X component of the left rope. What is pulling to the right? The X component of the right Y rope. Is anything moving? Well, no, traffic lights don't fall, right? So everything is equal to 0. We know everything's equal to 0, which means the X component of all the motion is equal to 0, and the Y component of all the motion is equal to 0. And the thing that always tricks people is you're still left with two unknowns, T1 and T2. So you kind of try to solve for one to get to the other, right? If you remember like replacement stuff from, I think this would be Algebra 2, I want to say, right? We can write our equation out, F net in the X equals T2 in the X minus T1 in the X, which equals 0, which means the X and Y components are equal to each other. And then if we solve them out, cosine 30, cosine 45, we can set them equal to each other to know that the tension in rope 2 is equal to 1.225 times the tension in rope 1. Does that make sense? Is the tension in rope 2 going to be stronger? Well, yeah, it's at 45-degree angle, right? It's 45 is the maximum angle to do things at. So if we have this equation where we know T1 in respect to T2, we can then solve the Y components because T1 and T2 are still the same thing, right? We know that the net force in the Y component is equal to the Y component of T1 and the Y component of T2 minus the weight, which is mass times gravity. Solve that all out, landing us at equation 4.73 here. Notice here, T1 and T2 are not the Y components of the total components because we did our trigonometry to solve those back into T1 and T2. Once we solve them back, we can substitute in T2, shown here in 4.73, with our equation from 4.70 to land us on something that only solves for T1, which is 4.74. Math it out, we land at a tension for rope 1, and then we can use that tension to solve the tension for rope 2. Cool. Again, it's that slow methodical approach. It's that drawing it out, think about what I'm talking about here. Remembering math I haven't used in a while, like replacing things to land on what I need to land on. So cool. The end of this, I want to go over some more advanced math, physics, pure physics stuff that we'll get to later, which is here, which is the 4 basic forces. In general, everything in the universe runs off of 4 things. Those 4 things are gravitational force, which is right what we all very familiar with. Electromagnetic force, which is the attraction and repulsion of, say, magnetism. A weak nuclear force and a strong nuclear force. I think, what was it? Like, strong nuclear force keeps like nucleuses together. I think a weak nuclear force keeps the atom together. I could be mistaken. I haven't discussed that stuff in a little bit. So, couple thoughts on these forces. First of all, gravitation is by far and away way stronger than everything else. It's the one that we know, right? We can't actually feel in any way, shape, or form the other 3 forces that kind of keep the universe together. 2, they all have like carrier particles and stuff like that, which is super complicated and will be lightly touched upon in this class. Gravitons, I don't even touch that stuff. But yeah, these concepts of these forces and how they interact with each other still, funny enough, like pay heed a bit to Newton's laws. This concept here is kind of where Einstein came in and made Newton's laws better equipped to describe the vastness is our reality, essentially. Newton ain't wrong in what he said, but you need to be more complicated with the math to explain stuff going down to strong and weak nuclear forces and stuff like that. So yeah, but all of these things still exist in our day-to-day lives. Gravity affects the way basketball players pass the ball, and strong and weak magnetic forces what goes on in CERN over in Switzerland, right? The particle accelerator that's like producing new particles of matter and stuff like that. Well, not producing new ones, but allowing us to understand and study them better. And everything we've been talking about here goes in so much to all the discussions that you have in other scientific classes, right? This picture here, very classic. Hopefully you've all seen this already. It's the picture of the supermassive black hole at the center of M87. It's an actual picture of a black hole. And if you've seen the movie Interstellar, you're going to kind of understand a bit about what we're looking at here and why the colors are important and why its shape matters. And all this stuff can be boiled back to the level of physics that we're talking about here and the interactions between the forces and stuff like that. I mean, it's super in-depth and super interesting. If you like this sort of conversation, there's many fantastic books by famous scientists that kind of go over this stuff at a layman's level, right? You don't need to have a textbook on particle physics to get an understanding of particle physics. So yeah, just a quick little side brief discussion on the expansiveness that the concept of forces can go into. So that is chapter 4, the lecture. Hope you enjoyed yourself. Comment down below if you have any questions, and I'll see you guys later.